All right, our last section in chapter 6, 6.7, talks about recursively defined sequences. Now, I'm going to be honest with you, this is not easy at all. It's confusing. So let's go back to two types of sequences. I want you to understand the difference between the two. So an explicit sequence is this. An explicit sequence is when you actually write something that you can get the nth term of anything. So for example, a sub n equals 5x plus 1. Now that's arithmetic. I'm going to put an A here for arithmetic. If I did a sub n equals 2 times 5 to the n minus 1, that's explicit, because in either one of these, if I wanted to know the 17th term in the sequence, you would take the 17, plug it in, and you would get the 17th term. Here, you would plug in the 17 and get the 17th term. So this is geometric, by the way. So that's explicit. Recursive is when you don't know, or you don't write a function based on the nth term of the sequence. What you do is you actually go through and you are given the first term and then how you get to the next term in the sequence. So it's, for example, it looks like this. The first term is 7, and then we take the term and we add 3 to get to the next term. So that's recursive. I'm giving you the 7th term, but to get to the 7th term. I'm giving you the first term is 7, but to get to the next term, I add 3. So the next term would be 10. The next term after that would be 13. And remember, this a sub n minus 1, if I want to find the a sub n term, that means the current term, I take the term before it and add 3. So if I wanted to find the second term, this means I would take the first term and I would add 3 to it. To get the 8th term, you would take the 7th term and add 3. But you can't just get the 50th term here. You would have to actually write them all out to get to the 50th term. So this is recursive. These are explicit. Here's what we're going to learn. You have to learn how to write terms of recursively defined sequences, how to write recursive rules for sequences. This is an important one. This is a whole standard on its own. How to translate from recursive to explicit and vice versa, and then how to write recursive rules for special sequences. So, first up, in this book so far, you have done arithmetic and geometric sequences explicitly. So again, an explicit rule gives a sub n as a function of the term's position n. So again, that's how you find any position, any term in the sequence, given the position. So for example, here it is. Skip this. Look at this. A sub n equals 2n plus 1. That function, if I wanted to know the first term in the sequence, I'd plug in 1 and I would get 3. If I plugged in a 2 for the second term of the sequence, I would get 5. If I plugged in the third term of the sequence, you would get 7, and so on. That's your sequence. You are now going to define arithmetic and geometric sequences recursively. A recursive rule gives the beginning term or terms, it could be more than one, of a sequence, and a recursive equation that tells how you get from to the next term knowing the term before it. And here is your core concept. For arithmetic, you have to give the beginning terms of the sequence. I can't stress this enough. Always, always, always give the beginning terms, because how do we know where we start if you don't give us the first terms? So you have to always give us the first or second or third terms. Here, it's a sub n equals a sub n minus 1 plus d. D is the common difference. That's all we need to plug in. We take the d, we plug it in, we're done. Here, we need the common ratio. We plug it in, we're done. But again, you have to always give at least the first term. All right, so let's look at example number 1. I want you to write the first 6 terms of the sequence. And this is what you're always going to do if you want to write an explicit formula from the recursive. So here's what it says to do. Notice what it does here. In A, it gives you the first term, which is 2. Then it tells you to get to the next term, you take the term before it and you add 3. So we know the first term is 2. The second term is, well, plus 3 would be 5. The next term would be 8. The next term would be 11, 14, and 17. Those are the 6 terms. Now, if you actually did write this out, this is important. A sub 1 equals 2. A sub 2, the second term. If we plug that into this formula, if we plugged in 2, 2 minus 1, right here, 2 minus 1 is 1. So that means we take a sub 1 plus 3. Well, a sub 1 we know is 2, so it'd be 2 plus 3, which gives me 5. To get to the third term, we take the second term plus 3. Well, the second term is 5, so that'd be 5 plus 3, and that gives me 8. So that's the work that you would do to actually plug it in and prove it. We take the term before it, we always add 3. Next one. This one says to take a sub n equals 3 multiplied by the term before it. In this case, the first term is 1. First term is 1. What does it say to do? Well, the common ratio is 3, so we multiply by 3 every time. Times 3, so it'll be 3. Yeah. Multiply by 3, multiply by 3, multiply by 3, multiply by 3. And there are the first 6 terms of that sequence. First one is arithmetic, second one is geometric. Now, it also says to graph it. All you would do is graph, like in the first one, 1, 2, 2, 5, 3, 5, or 3, 8. You just graph it as dots on graph paper. Now, looking at recursive rules. Recursive rules. Write a cursive rule for the sequence. So, here we go. Writing a recursive rule. Step 1, let's figure out what's happening. I'll let you figure this out. What's happening each time here? From negative 30 to negative 18. From negative 18 to negative 6. From negative 6 to positive 6. From 6 to 18. Hopefully you can figure out that you're adding 12 each time. That means it's arithmetic sequence, and we have a common difference of 12. So, the recursive rule would be this. A sub n equals a sub n minus 1, and then we add 12. That's how you get to the next term. The problem is, you have to give the first term in order to know what we're doing. If you're adding 12 to the term, well, where do we start? Do we start at 5? Do we start at the term number 7? Do we start at negative 3? So in this problem, we have to give us the first term. The first term is negative 30, and to get to every term after that, we add 12. That's a recursive rule. Now, on this sequence, 500 to 100 to 20 to 4, we are dividing by 5, which is the same as multiplying by 1/5. So this is a geometric sequence where the first term, we have to give the first term as 500, and then every term after that, we multiply by 1/5. So we plug it into our formula, which is the common ratio, which is r. So r is 1/5, multiplied by a sub n minus 1. Now we don't need the parentheses, actually, I'd rather not. Let's actually erase that here. And there we go. So a sub n minus 1. And there is my rule. All right, you have a problem like this on your test. I am going to give you a recursive rule, and you need to write an explicit rule from that. So, A, they give you the first term as 25, and then to get to every other term, we subtract 10. The very first thing we have to do is we have to write out the sequence. So the first term is 25. If we subtract 10, the next term is 15. The next term is 5. The next term is negative 5, and so on. The reason why we do this is it'll help us write in our explicit rule. So remember, our explicit function is a sub n, or our explicit equation is a sub n equals our first term plus n minus 1 times our common difference. Now, notice what I did here. I wrote this out, and the reason I do that, it's not really, you don't have to do it, but it will help you understand what you're doing here. What's our first term? Well, it's 25. Our common difference is negative 10. So now we just simplify. If I distribute the negative 10, and I combine like terms and simplify, there's my function, my equation. A sub m equals negative 10n plus 35. All right, going to our next one, let's write a rule based from this recursive rule. Now, by the way, you'll hear me say a lot, explicit rule, recursive rule. That's just an equation. So the next one, this right here is geometric. So, if you looked at your first term, it'd be 19.6. The second term would be multiplying by negative a half, or negative 0.5. And you could continue that on. But we need our r value, which is negative a half, and our first term. If we plugged it in to our formula, it would be first term multiplied by negative a half to the n minus 1 power. And that's the rule for geometric sequences that are explicit rules. That's it. If you wanted to find the 50th term, you would just plug in 50 there and get it from there. In example 4, we're going to go the opposite way. I want to write a recursive rule from each explicit rule. This is where you actually have to plug in some values, but you have to get your sequence from this. And so all you do is, to find the first term, we plug in a sub 1. So if we plug in 1, negative 2, multiplied by 1, plus 3 is 1. So the first term of the sequence would be 1. Now if we plug in the second term, that'd be negative 4 plus 3 would be negative 1. We plug in the third term, that'd be negative 6 plus 3, negative 3. We plugged in the fourth term, negative 5, and so on. Because we have to do that to determine, is it arithmetic sequence or is it a geometric sequence? And we have to find the D or the R. So we know the first term is 1. Is this geometric or is this arithmetic? It's arithmetic. It's going down by 2 every time. So we know the D value is negative 2. So we use these values right here to plug it into our formula. We know our first term is 1. That's all we need to start this sequence. And then the rest of it is just plugging it in. Plus negative 2, which would just be minus 2. And there is my answer. The next one. Our first term is negative 3. And then every time we multiply by 2, we double it, because this is exponential. So negative 6, negative 12, negative 24, and so on. So we just plug it into our formula. A sub m equals 2, and then a sub m minus 1. That's it. Our last example is one where you're doing like a special type of sequence. So writing recursive rules for special sequences. You can write recursive rules for sequences that are not arithmetic or geometric. So this is important. Not all sequences are arithmetic or geometric sequences. But as long as you can find a pattern, you can write a recursive rule. So here's our example. By the way, you do have one of these on your test. In this sequence below, I just want you to pause the video, see if you can find a pattern. Can you find a pattern from that sequence? Well, if you looked at it, to get this term, the third term, you would add the 2 terms before it. To get the fourth term, number 3 here, like the number 3, you would add 1 plus 2. And then 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is 13. So Actually, let's just do part B, because B is just finding the next three terms. So it would be 13. 8 plus 13 is 21. And 13 plus 21 is 34. So the next three terms of the sequence would just be 13, 21, and 34. Now, to write your recursive rule, what do? Well, I have to find the nth number. So how do you get to the nth number? You add the two terms before it. So remember, a sub n would be the current number we're on. A sub n minus 1 is the term before that. A sub n minus 2 would be the term before that. So I need, anytime you pick a number, you have to pick the two terms before it and add them together. So I could do a sub n minus 1 plus a sub n minus 2. What does this mean? This means you take the number before this one and the number before that one and add them together. So we take the two numbers and add them together before the current number we need to find. The problem is I actually have to give you the first two numbers. You can't get either one of these ones on your own. You have to be given them. So you have to say a sub 1 equals 1 and a sub 2 equals 1. And there's your answer. So, again, if we give me these two numbers, the first two numbers in the sequence, the next number says to take those two numbers and add them together. And you just keep doing that same pattern. So this is a recursive rule for your special sequence.